Part A, define impulse. So impulse we can just define using the impulse momentum theorem. So either we can write impulse is the product of force and time, or impulse is the change in momentum. For the B part, it is mentioned that a chicken's egg of mass 58 grams is dropped onto grass from a height of 1.1 meters. The egg does not bounce or break. We have to figure out the kinetic energy of the egg just before the impact. So let's draw a diagram. So we have a chicken, let's say of chicken's egg of mass m. It is dropped onto grass from some height, and that height is 1.1 meters. We have to figure out the kinetic energy of the egg just before impact. So there are two ways to do it. Either we use the law of energy conservation or using the Stewart equation. Let's use both the methods. Method number one, the law of energy conservation. So let us label point A is the topmost point and point B is just before impact with the ground. So according to the law of energy conservation, total energy at A should be equal to total energy at B, which means kinetic energy at A plus potential energy at A should be equal to kinetic energy at B plus potential energy at B. Now, since the egg was dropped, so initial velocity is 0, kinetic energy at A is 0. Potential energy formula is mgh, so we will write down mgh, where the value of h is 1.1 meters. This will be equal to the kinetic energy just before the impact, which we are supposed to figure out. Let's write that as x plus. Since the point B is almost on the ground, we will assume the potential energy at the point B to be 0. So x plus 0. Hence the value of x, which is kinetic energy at B. This is equal to m into g into h. So what's the mass? 58 grams. So let's write it down. 58 into 10 to the power minus 3 in kilograms multiplied by 9.8 multiplied by height is 1.1. So if we simplify this, we will get the value of kinetic energy just before the impact to be 0.625 joules, which is what the question wants us to find. So the approximately the answer is 0.6 joules. We could have solved the same question using Stewart equation. So if I consider point A to B, let us use v square is equal to u square plus 2as. Let's do that. V square is equal to u square plus 2as along the y direction. So initially, since the egg was dropped, initial velocity we will write as 0 plus 2 times acceleration is negative 9.8 and displacement, which is the height in this case, which will be negative 1.1. Why minus? Because the egg is going downwards, displacement is downwards. That's why we put a negative sign. Hence, we will write v square to be 2 into 9.8 into 1.1. Now, since we have to figure out the kinetic energy, so we have the formula for kinetic energy as half mv square, which we can write as half into mass is 58 grams, which you need to convert in kilograms, multiplied by the value of v square was this. So 2 into 9.8 into 1.1. So if we simplify this expression, we will get 0.625 joules as the answer, which is the same which we got in method number one. So there are two methods to solve this question. Law of energy conservation, which is the faster and the easier method, and method 2 is the Stewart equation. In the second part, it is mentioned that the egg comes to rest in a time of 55 milliseconds. We have to determine the magnitude of the average decelerating force that the ground exerts on the egg. So we have to figure out the force that the ground exerts on the egg. By definition, this is the normal reaction. So the normal reaction which the ground provides to the egg. So let's draw the diagram again. So we have a chicken egg of mass m, which was dropped from a height of 1.1 meters onto the ground. Now the egg travels 1.1 meter distance downwards until it hits the ground. So it is given that the egg comes to rest in a time of 55 milliseconds. So please do not think that this 55 milliseconds is the time taken for the egg to go from the top to the ground. That's not the time. The 55 milliseconds is the time of contact with the ground. Let me explain. So imagine if the egg travels 1.1 meters and it is just about to hit the ground. So let me draw a egg at the bottom. So it is very close to the ground, just about to hit the ground. So which means it will be traveling with some speed v. Now, once the egg makes contact with the ground, after some time, the egg comes to rest. So we can say final velocity of the egg will be zero. It is mentioned that the egg does not bounce and it does not break also. So the final velocity of the egg after the impact will be zero. And the time taken for the velocity to change from v to zero is 55 milliseconds. And we need to figure out once the egg makes the contact with the ground, how much force the ground exerted on the egg. So if we draw the free body diagram of the egg when the egg is in contact with the ground, we have mg, the weight of the object, always acting downwards, and then we have the normal reaction acting upwards. Now, ordinarily in normal situations, when the egg is kept on the ground, normal reaction and mg will be equal to each other. But in this case, the egg is traveling from some height and then it is traveling at a very high speed and it impacts the ground, it hits the ground. So normal reaction will not be equal to mg. In fact, normal reaction will be a lot greater than mg. And the question wants us to find the force that the ground exerts on the egg, which in other words is normal reaction. So how do we figure out the normal reaction? We again go to the impulse momentum theorem, which states that J is equal to Ft equals to change in the momentum. But the catch here is J is equal to F delta T. F is not just any force. F is the net force which is acting on the object. So in this case, if you look at the free body diagram, mg weight is acting downwards and the normal reaction is upwards. So the net force will be N minus mg. So that will be the value of J. So let's write down J will be equal to N minus mg, which is the net force multiplied by time. The time of contact is 55 milliseconds, which is given. So let's write down 55 into 10 to the power minus 3, which will be equal to m into final velocity minus initial velocity. Final velocity of the egg is 0 because the egg has come to rest. And v initial we need to figure out. And what is initial velocity in this case? It is the velocity of the egg just before it hits the ground. So initially the velocity was 0 at the top, and just before hitting the ground, its velocity v. Now, in the previous question, we had figured out the value of v. Now, in the previous part, we had figured out the value of kinetic energy to be 0.625 joules. So, we can write that as half mv square, where mass is 58 grams. So, which is 58 into 10 to the power minus 3. So, let's write this in one equation. 0.625 will be half into 58 into 10 to the power minus 3 multiplied by v square. And if you simplify this equation and try to get the value of v as 4.64 meters per second, this will be the initial velocity which we can write in this expression. So the value of j, which was f into delta t, which is equal to change in the momentum, we will write that as m is the mass. So let's write that as 58 into 10 to the power minus 3. Final velocity being 0. Initial velocity we have just calculated to be 4.64. So let's write that in. Now all we need to do, let us simplify only the right side of this expression. So if we figure out an answer, we will get 0.269 with a minus sign. That's the value of J impulse. Now, if we go back to the question, we were supposed to find the magnitude of the force. And that is why this minus sign we can ignore since we want only the magnitude. So the entire equation we can write now as N minus mg multiplied by the time taken, which was 55 milliseconds. 55 into 10 to the power minus 3. This will be equal to, on the right hand side, ignoring the minus sign, we'll get 0.269. And now let us cross multiply. N minus mg will become equal to 0.269 in the numerator, and in the denominator we have 55 into 10 to the power minus 3. So if we solve the right hand side of this equation, we will get 4.9. Hence, n minus mg is equal to 4.9, which we can write as n is equal to mg plus 4.9. Now, mass of the object egg in this case was 58 grams. So we'll write 58 into 10 to the power minus 3 multiplied by 9.8 plus 4.9. So if we solve this, we will get 5.468 Newton as the value of this normal reaction. And if we approximate this to two significant figures, we will write the value of normal reaction to be 5.5 newtons. So this is the value of the normal reaction. But the question was asking us to find the force that the ground exerts on the egg. So be careful. What the question is asking you to find is nothing but the normal reaction, which we have figured out as 5.5 Newton. So that's how we solve such questions. So let us revise what was the key factor which we were using here. When you are using the impulse momentum theorem, whenever you use this formula, remember F is not just any force, it is the net force acting on the object. So in this case, when the egg hit the ground, it not only has the weight which is acting downwards, it also has a normal reaction which is provided by the ground. That is what we were supposed to find in this question. In the third part, we have to explain why the egg is likely to break when dropped onto concrete from the same height. So we'll have to use the same impulse momentum theorem, the J is equal to force into time. Now, since we have to prove that the egg is likely to break when dropped onto concrete, which means the force which the concrete is providing to the egg is much larger than as compared to the ground. So how do we prove it? So the value of F delta t is equal to change in the momentum, which is equal to m final velocity minus initial velocity. Now, since the egg is supposed to come to rest after hitting the surface, so final velocity is 0. Let's write that down. And initial velocity is the velocity of the egg just before hitting the surface. And in the previous case, we had figured out the value of that V to be 4.64 meters per second. So V initial is 4.64. So if you analyze, the right side of this expression is a constant because m final velocity, initial velocity are all the same no matter what the surface is. It could be the ground or it could be concrete, but the initial velocity and the final velocity are the same. So the right side of this expression is a constant. So we can write F delta t is a constant for both cases, concrete as well as ground. Now, since F into delta t is a constant, we can write force is inversely proportional to time. Now, try to visualize when the egg hits a concrete surface versus a egg hits the ground. The time taken to come to rest will be greater in which case? See, concrete is a lot harder surface, so the egg will come to rest in a very short amount of time. So we can write that the time taken in case of concrete, the time taken for the egg to come to rest when it hits the concrete will be much lesser than the time taken in case of the ground. So T concrete is less than time of the ground. Since force is inversely proportional to time, we can now deduce that the force in case of concrete will be greater than force in case of ground. So let me repeat. According to this deduction, the force which the egg experiences because of concrete, that will be much larger as compared to the force which is acting on the egg due to the ground. That is why when an egg hits a concrete surface, because the force is large, it is much likely to break in case of concrete as compared to the ground. And that's how we solve this question. Let me repeat what we have done. Initially, we proved that the right-hand side, which is delta P, is constant in both cases, concrete as well as the ground. Since the right-hand side is a constant, we can say force is inversely proportional to time. And that is the approach we use to solve this question.